Determinants, adjoint and inverse of a matrix. In this video, we are going to learn about adjoint and inverse of a given matrix. That is the objective of today's class. So, to find the inverse of a given matrix, we shall first define the adjoint of a matrix. Definition: the adjoint of a square matrix A equal to matrix small aij over n cross n. So we are defining the adjoint for a square matrix A. You know the definition of a square matrix. In a square matrix, the number of rows will be equal to the number of columns. So we consider a square matrix A. Let A be any square matrix of order n. Okay, here number of rows equal to n and number of columns is equal to n. Both are equal. So it's a square matrix of order n. We are considering a square matrix A of order n. Okay. So the adjoint of a square matrix A equal to matrix small aij over n cross n. The elements of capital A are small aij's. Okay, is defined as the transpose of the matrix capital Aij over n cross n. So the adjoint of a square matrix A is the transpose of the cofactor matrix. Capital Aij means capital Aij is the cofactor of this element small aij. Okay, so adjoint of a square matrix A is nothing but the transpose of the cofactor matrix capital Aij over n cross n. Where capital Aij, what is capital Aij? Capital Aij is here the cofactor of the element small aij. Okay, so this is the definition of adjoint of a square matrix A. And the adjoint of the square matrix A is denoted by the symbol adj. The first three letters ADJ, adj. Okay, the first three letters of adjoint are ADJ, adj A. Okay. Next remark: for a square matrix of order 2 given by A equal to matrix A11, A12, A21, A22. Here we consider a square matrix of order 2, number of rows equal to 2 and number of columns equal to 2. There are two rows, A11, A12 is the first row. In the second row we have the elements A21 and A22. Okay. The first column we have the elements A11, A21. This is the first column, and the second column elements are A12, A22. So there are two rows and two columns. So it's a square matrix of order 2. Okay, it's a square matrix of order 2. Now consider this square matrix of order 2. Now I am going to write the adjoint A, adjoint of the given matrix A. How to write that? It's a square matrix of order 2. So we can write the adjoint A directly. We can write adjoint A for the given matrix A directly. How to do that? Adjoint A can also be obtained by interchanging the elements A11 and A22. Okay, so first we have to interchange the elements given in the positions A11 and A22. So interchange these two elements A11 and A22. Okay, and by changing the signs of A12 and A21. Next step is you have to change the signs of the elements given in the position 1, 2 and 2, 1. Okay, here we need to change the signs of these two elements A12 and A21. Therefore, adjoint A is equal to A22 minus A12 minus A21 A11. Here I have changed the elements. See the diagonal A22 and A11. I have interchanged these two elements A11 and A22, and I have changed the signs of these two elements A12 and A21. So this is the adjoint A for the given matrix A, right? Example 1. Find adjoint A for A equal to matrix 2, 3, 1, 4. It is a square matrix of order 2 because we see there are two rows 2, 3, 1, 4 and there are two columns 2, 1, 3, 4. Right. So here we are asked to find adjoint A for the given matrix A. See the solution. What is the definition of adjoint A? Adjoint A is the transpose of the cofactor matrix. So we have to find the cofactors of A11, A12, A21, A22. Okay. In 1 position we have the element 2. So first we find the cofactor of 2. Okay, our cofactor of small a11. What is the cofactor of small a11? It is capital A11. What is the definition of cofactor of small aij? Cofactor of small aij is capital Aij. Okay, so capital Aij is equal to minus 1 whole to the power I plus j. I plus j into the corresponding minor mij. This is the definition of cofactor of small aij. Okay, using this definition we find a11. Okay, what is a11? Capital A11 is minus 1 whole to the power I plus j. What is I plus j? 1 plus 1. In the place of I we have 1. In the place of j also we have 1. So 1 plus 1 into the corresponding minor is m11. Okay. We are finding the cofactor of the element 2. Okay. So delete the row and the column having the element 2. We get 4. So m11 is 4. Right. So what we are getting is minus 1 whole square into 4. What is minus 1 whole square? It is plus 1. So you are getting 4. Okay, so A11 equal to 4. Similarly, let us find A12. Cofactor of small a12 is capital A12 and this is minus 1 whole to the power 1 plus 2. Okay, 1 plus 2 into the corresponding minor M12. And this is minus 1 whole cube. We are finding the cofactor of the element 3, that is in A12 position we have the element 3. So we have to delete the row and the column having the element 3. You will be getting 1. Okay. So this is minus 1 whole cube into 1. What is minus 1 whole cube? Minus. So minus 1. Okay. Next, cofactor of small a21 is capital A21. Again, by definition, this is minus 1 whole to the power 2 plus 1. What is 2 plus 1? 3 into m21. What is m21? Now we are finding the cofactor of the element 1. So we have to delete the row and the column having the element 1. You will be getting 3. So this is minus 1 cube into 3 or minus 3. Okay. Similarly, cofactor of small a22 is capital A22 and capital A22 is minus 1 whole to the power 2 plus 2. Okay, 2 plus 2 is 4 into m22. What is m22? We are finding the cofactor of the element 4. So delete the row and the column having the element 4. You'll be getting 2. So this is minus 1 whole to the power 4 into 2 or 2. Okay, but what is adjoint A? Adjoint A is the transpose of the cofactor matrix. Okay, so this is A11. First column is A11. A 12, then A21, A22. Okay, therefore we get 4 minus 1 minus 3, 2. Example 2. Find adjoint A for the matrix A equal to 1, 3, 3, 1, 4, 3, 1, 3, 4. It's a square matrix of order 3 because there are 3 rows and 3 columns. Here we are asked to find adjoint A for the given matrix A. So we have to find the cofactor elements of A11, A12, A13, A21, A22, A23, A31, A32, A33. First, let us find the cofactor of small a11. Okay. So, cofactor of small a11 is capital A11. What is capital A11? Capital A11 is here 16 minus 3. Okay, because in small a11 position we have the element 1, so we have to delete the row and the column having the element 1. You'll be getting 2 by 2 matrix 4 3 3 4. So 16 minus 9 gives 7. Okay. So by definition, this is minus 1 whole to the power 1 plus 1. Okay. 1 plus 1 is 2 into the corresponding minor M11. It is minus 1 the whole square into 16 minus 9 is 7, right? So what you are getting is 7. Next, cofactor of small a12. In small a12 position I have the element 3, so delete the row and the column having the element 3. Okay, so by definition capital A12 is minus 1 whole to the power 1 plus 2. Capital A12 is minus 1 whole to the power 1 plus 2 into the corresponding minor M12, right? So this is minus 1 cube. What is minus 1 cube? It is minus 1. Okay, minus 1 into what is M12? Delete the row and the column having the element 3. So you'll be getting 1314. Okay, so what are getting is 4 minus 3. 4 minus 3, it is 1. So minus 1. Next, cofactor of the element small a13. Okay, it is capital A13. So capital A13 is by definition this is minus 1 whole to the power 1 plus 3. What is 1 plus 3? It is 4 into the corresponding minor is M13. Okay, so what is minus 1 whole to the power 4? It is plus 1. What is M13? We are finding the cofactor of the element 3. Okay, in 1 3 position we have the element 3. So we are finding the cofactor of 3. Delete the row and the column having the element 3. You are getting a 2 by 2 matrix 1 4 1 3. So in the downward arrow you are getting 3 minus upward arrow, so minus 4. What is 3 minus 4? It is minus 1. Okay, so minus 1. A13 is minus 1. Similarly we can find 821. What is 821? 821 is minus 1 whole to the power 2 plus 1. Okay, so 3 into M21. What is M21? We are finding the cofactor of the element 1. Okay, so delete the row and the column having the element 1. We'll be getting 3, 3, 3, 4. So using the definition of a determinant, expand this, you will be getting 12 minus 9. So this is 3. Okay, so what you are getting is minus 3. Similarly, we can find 822, it is 1, 823 is 0, 831 is minus 3, 832 is 0, 833 is 1. Okay, therefore adjoint A. What is adjoint A? Transpose of the cofactor matrix. Okay, so how will you write? The first column is A11, A12, A13. This is the first column elements, and the second column elements are A21, A22, A23. Okay, then third column elements are A31, A32, A33. Okay, so adjoint A is the transpose of the cofactor matrix. So what is adjoint A here? 7 minus 3 minus 3 minus 1 1 0 minus 1 0 1. See the next definition. Definition 1. A square matrix A is said to be singular if determinant A equal to 0. Okay. A square matrix A is said to be singular. Singular means determinant A is 0. Value of the determinant is 0 means we say that the given square matrix A is a singular matrix. Okay. For example, if you find the determinant of the matrix A equal to matrix 1 to 4 8. Okay, if you find the determinant of the given matrix, then what you are getting, C in the downward arrow you are getting 8 minus upward arrow. In the upward arrow also you are getting 8. So 8 minus 8 is 0. So what you are getting? 0. So what we can say? The given square matrix A is a singular matrix. Okay. Next, definition 2. A square matrix A is said to be non-singular. A square matrix A is said to be non-singular. Non-singular means if determinant A is not equal to 0, value of the determinant is not equal to 0. It should not be equal to 0. For example, consider the matrix A equal to minus 1, 2, 4, 8. Okay, it's a 2 by 2 matrix, square matrix of order 2. Okay, so what is the determinant of A? In the downward arrow you are getting minus 8. In the upward are also you are getting minus 8. So what you are getting? Minus 16. Minus 16 is obviously not equal to 0. Okay, so this is a non-zero value. So what we can say? The given square matrix A is a non-singular matrix. Okay. Next, we state the following theorems without proof. Okay, we state the following results without proof. What is result 1? If A is any square matrix, if A is any square matrix of order n, then what is the result? A into adjoint A. Okay, A into adjoint A is equal to adjoint A into A equals A into determinant I. Okay, so this is the first result. Okay, what is the given statement here? A is any square matrix of order n. A should be a square matrix of order n. That means in the given matrix, the number of rows must be equal to the number of columns. Okay, then we can define like this: A into adjoint A, the product of A and adjoint A, okay, is equal to, write in reverse order, adjoint A into A, the product of adjoint A and A is equal to A into determinant I. Okay, what is I here? I is an identity matrix of order n. I is an identity matrix of order n. So this is the first result. A into adjoint A equals adjoint A into A equals A into determinant I. So for a square matrix A, we have this result. Okay, A into adjoint A is equal to adjoint A into A is equal to A into determinant I. What is the next result? If A and B are two non-singular matrices of the same order. What do you mean by non-singular matrices? Just now we have discussed the definition of non-singular matrix, right? If A is a non-singular matrix means then the value of the determinant A should be not equal to 0, right? So if A is a non-singular matrix means determinant A is not equal to 0. That is the condition. Here A and B are non-singular matrices. Okay, this is the given condition. A and B are both non-singular matrices, which means that determinant A is not equal to 0 as well as determinant B is not equal to 0. Okay, and both are of the same order, right? If this condition is satisfied, then we have AB and BA are also non-singular matrices of the same order. Okay, AB and BA, the product AB and the product BA are also non-singular matrices, which means that determinant AB is not equal to 0 and determinant BA is not equal to 0 of the same order. So what is the next result? If determinant A is not equal to 0 and determinant B is not equal to 0, then the product determinant AB is not equal to 0 and determinant BA is not equal to 0. So this is the second result. And the third result is the determinant of the product of matrices. Okay, the determinant of the product of matrices is equal to the product of their respective determinants. How will you express it? Determinant AB. Okay, determinant of the product of matrices. So AB. Okay, product AB is equal to product of their respective determinants. So determinant A into determinant B, where A and B are square matrices of the same order. Here A and B are square matrices of the same order. And the next result is a square matrix A is invertible if and only if A is non-singular matrix. Very important result. A square matrix A is invertible. Invertible means inverse. Okay, so if the given square matrix A has an inverse, okay, if A inverse exists, if and only if A is non-singular matrix. So A inverse exists means A must be a non-singular matrix. This is the direct part, if part. Okay, what is the converse part here? If A is a non-singular matrix, then A must be, then A has an inverse. Then A has an inverse. A inverse will exist. Okay. So that is the statement given here. If A inverse exists, then A must be a non-singular matrix. That is the direct part. If A inverse exists, then the given square matrix A is a non-singular matrix. That means determinant A is not equal to 0. This is the direct part. What is the converse part? If the given square matrix A is a non-singular matrix, that is determinant A is not equal to 0 means then A inverse will exist. A inverse will exist. So this is the condition for the existence of inverse of the given matrix. Okay, this is the condition for the existence of inverse of the given matrix. Okay, A inverse exists if A is a non-singular matrix. The given square matrix A is a non-singular matrix. That is determinant A is not equal to 0. If A is a non-singular square matrix, which means the determinant A is not equal to 0. If determinant A is not equal to 0 means then A inverse will exist. So this is the condition for the existence of the inverse of a given square matrix. Okay. So that is the result given here. A is invertible and A inverse. Invertible means how will you represent it? A inverse. Okay. So A inverse equal to 1 by determinant A into adjoint A. 1 by determinant A into adjoint A. This is the result for finding A inverse. Okay. Suppose A is a square matrix of order n means then A inverse formula is 1 by determinant A into adjoint A, provided A must be a non-singular matrix. Determinant A should be not equal to 0, should be non-zero, right? So that is the condition. So in general, if A is a square matrix of order n, then determinant adjoint A. Okay, determinant of adjoint A is equal to determinant A to the power n minus 1. Determinant A to the power n minus 1. This is one of the results we have to remember. See problem 1. If matrix 1 3 3 1 4 3 1 3 4. This is the given matrix. Okay. So it can be taken as A. It's a square matrix of order 3 because we see 3 rows, right? 3 rows and 3 columns. Okay. Then we have to verify that A into adjoint A, the product. Okay. A and adjoint A is equal to determinant A into I. Also find A inverse. So this is the question given here. What is the first part? We have to verify A into adjoint A is equal to determinant A into I. Okay, using that condition, we have to find A inverse. Also find A inverse means we have to deduce A inverse from the given result. A into adjoint A is equal to determinant A into I. That is the meaning here. Now let us discuss the solution. What is the first part given here? We have to verify that A into adjoint A is equal to determinant A into I. So first we have to find determinant A. What is determinant A? Determinant A is equal to expand this matrix. So 1 into, we have to delete the row and the column having the element 1. So you'll be getting 16 minus 3. Okay. Into 3 is 9. So 16 minus 9 minus 3. Okay. What is the first row? We are expanding along the first row. Okay, so 1 into 16 minus 9. Next element is in 1 2 position we have the element 3. This is 1 2 position, so we'll be getting minus sign. Minus 3 into, delete the row and the column having the element 3. So we'll be getting 4 minus 3. Okay, in the downward arrow it is 4 minus, in the upward arrow 3. So 4 minus 3 plus, the next position is 1 3 position, so we will be having plus sign. The next element is 3. So 3 into, delete the row and the column having the element 3. So what are getting? 1 4 1 3, 2 by 2 matrix. So expand this. In the downward arrow you will get 3 minus, in the upward arrow you will get 4. So 3 minus 4 is minus 1. So on simplification, we are getting 1. 1 is obviously not equal to 0. So determinant A is not equal to 0 means A inverse will exist, right? Next, we have to find adjoint A. Already we have found adjoint A for the given matrix. We have already discussed this. Okay, so adjoint A means how will you find? Adjoint A is nothing but the transpose of the cofactor matrix. So we have to find all the cofactors. Here, cofactor of 1 or small a11 is capital A11, it is 7. And cofactor of small a12 is capital A12, it is -1. Cofactor of small a13 is capital A13, it is -1. Next, cofactor of small a21 is capital A21, it is -3. Cofactor of small a22 is capital A22, it is 1. Cofactor of small a23 is capital A23, it is 0. Cofactor of small a31 is capital A31, it is -3. Cofactor of small a32 is capital A32, it is 0. Cofactor of small a33 is capital A33, it is 1. Already we have discussed this, how to find cofactors, right? So I am writing it directly here. Therefore, adjoint A is the transpose of the cofactor matrix. So the first column is 7 -1 -1. The second column is -3 1 0, and the third column is -3 0 1. This is the adjoint matrix. Okay. Next, I am going to verify that A into adjoint A is whether A into adjoint A is an identity matrix. I am going to verify that. So I am going to take the product of A and adjoint A. This is the given matrix A 1 3 3 1 4 3 1 3 4, and this is the matrix of adjoint A 7 -3 -3 -1 1 0 -1 0 1. So I am going to take the product of these two matrices. Okay. How will you take the product? First row with first column. How will you multiply first row with first column? Okay. So 1 into 7 is 7. Minus 1 into 3 is -3. That is the first element. Okay. Then 3 into -1 is -3. Okay. So fix the first row in the first matrix. Okay. So first row, first column gives you the first element. Then first row, second column gives you the second element, that is 1 2 position. It is 1 into -3, -3. Okay. Then 3 into 1, 3. So plus 3. 3 into 0 is 0. So plus 0, right? Then first row, third column. Okay, first row, third column. So -3 into 1 is -3. 3 into 0 is 0. So plus 0. Then 3 into 1 is 3. So plus 3. Okay, so first row is over. Then fix the second row. Like that, I have to fix the third row. Second row, first column gives you the 8 to 1 position. So 7 into 1, 7. -1 into 4 is -4. 3 into -1, -3. Okay. Then second row, second column, 1 into -3, -3. 4 into 1, +4. 3 into 0, 0. Okay. Then second row, third column. So -3 into 1, -3. 4 into 0, 0. Okay. Then 3 into 1, +3. Right. So plus 3. So second row is over. Now fix the third row. Third row with first column. So 7 into 1, 7. -3, -4. Okay. Then 1 into -3, -3. 3 into 1, 3. 0. Then third row, third column. So -3, 0 plus 4. Now simplify. On simplification, 7 minus 6 is 1. This becomes 0. Minus 3 plus 3 plus 0 is 0. Then here also you'll get 0. Minus 3 plus 3 becomes 0. Here 7 minus 7 is 0, right? Then here 4 minus 3 is 1. Here minus 3 plus 0, so 0. Then third row is 7 minus 7, 0. Here minus 3 plus 3 gives you 0. Here we have 4 minus 3, it is 1. So what you are getting is identity matrix, right? Identity matrix of order 3. So the product A and adjoint A gives you identity matrix. Okay, so how will you rewrite that? 1 into 1 0 0 0 1 0 0 0 1. So I can rewrite here 1 into, okay. Actually what I am getting is 1 0 0 0 1 0 0 0 1 in the previous step. In the next step I am rewriting it as 1 into, okay, 1 into 1 0 0 0 1 0 0 0 1. Why I have written like this? Because I have to prove that A into adjoint A is determinant A into I. A into adjoint A is determinant A into I. So in order to get this result, I have rewritten it as 1 into, because if I write 1 into the matrix, then I can replace this 1 by determinant A, because determinant A value is 1. Value of determinant A is 1, right? So that should be replaced by determinant A here. So determinant A into what is this? This is an identity matrix of order 3. So determinant A into I. So first part we have verified. Okay, using that condition we have to find A inverse. What is A inverse formula? A inverse will exist only if determinant A is not equal to 0. A is a non-singular matrix. Okay, here already we have verified that in the first step we have check that A is a non-singular matrix. Determinant A is not equal to 0. So we are able to find A inverse. What is the formula for A inverse? A inverse is 1 by determinant A into adjoint A. Okay, so substitute everything. Already we have found adjoint A and determinant A. Determinant A value is 1. This is adjoint A matrix. Okay, so 1 by 1 into this. So if you multiply the matrix with the element 1, with 1 you will be getting the same matrix only, right? So 7 minus 3 minus 3 minus 1 1 0 minus 1 0 1. So this is your A inverse, right? So problem 1 is over. Now we move on to problem 2. What is problem 2? Show that the matrix A is equal to matrix 2 3 1 2 satisfies the equation A square minus 4A plus I equal to O. What is O here? O is a zero matrix. O means O is a zero matrix. What is I here? I is an identity matrix of order 2, because the given matrix is of order 2. So I is also of order 2. Okay, O is also of order 2. Using this equation we have to find A inverse. So first part is we have to verify that, or we have to show that the given matrix A satisfies the matrix equation. This is not an ordinary equation, it is an matrix equation. Okay, it is not an ordinary equation, it is a matrix equation. So we have to verify that the given matrix A satisfies the equation. Satisfies means if you substitute the value of A square A in this equation, then you have to get zero matrix. Okay, so when you substitute the value of A square A I in this equation in the left hand side, then you have to get zero matrix of order 2. Okay, so that is the first part. Then using that equation we have to find A inverse. We should not find A inverse directly here. Using this equation, via this equation only, we have to find A inverse. So this is the question given here. Let us discuss the solution. So first I am going to verify that whether this equation is satisfied or not. Okay, so I have to find A square first. Okay, so A square can be written as A into A. What is A? A is a given matrix. It is 2 3 1 2 of order 2 square matrix, right? So 2 3 1 2 I am multiplying here. Okay, matrix multiplication, first row with first column gives you the first element. Okay, so it is 2 into 2 4 plus 3 into 1 3. Then first row second column. So 3 into 2, 6 plus 3 into 2, 6. First row is over. Now fix the second row. So 1 into 2, 2 plus 1 into 2, 2. Then second row, second column. So 1 into 3, 3 plus 2 into 2, 4. So what you are getting is 7, 12, 4, 7. Okay. So substitute everything in the matrix equation. This is the value of a square minus this is the value of 4a. Okay, I have multiplied the given matrix A with the element 4. So what you are getting is 8, 12, 4, 8 plus identity matrix of order 2 is 1, 0, 0, 1. Now verify that 7 minus 8 is minus 1. Minus 1 plus 1 gives you 0. Okay, here 12 minus 12, 0, so 0. Then element wise operation here we are doing 4 minus 4 0, then 7 minus 8 minus 1 plus 1 0. So what are getting is 0 matrix of order 2, so it is O. Okay, so we have verified that a square minus 4a plus I equal to 0 matrix. Okay, now a square can be written as a into a. Using this equation, I have to find a inverse, right? So what I am doing is I am rewriting this equation as a square as a into a minus 4a. Bring this plus I to the other side, to the right hand side. So you will get minus I. Okay, now post multiplying this equation by a inverse on both sides. Okay, so a into A inverse minus 4A into A inverse equal to minus I into A inverse. I am post multiplying the given equation on both sides by A inverse. Okay, because I need A inverse. I need to find A inverse. Okay, now group like this. A into, you have to group the other two matrices. A into A inverse as like this minus 4I. A inverse in the previous slide we have minus A inverse in the right hand side. Okay, so minus A inverse. Now what is A into A inverse? It becomes I. So AI minus 4I is equal to minus A inverse, or A inverse equal to, you multiply this by minus, so you'll get 4I minus A. What is A into I? A into identity matrix is the same matrix A. So 4I minus A. Therefore, A inverse equal to, what is 4I? How will you write? 4 into identity matrix of order 2. So 1, 0, 0, 1 minus A. A is the given matrix. Okay. So when you subtract this matrix from 4, 0, 0, 4, then you will get 2 minus 3 minus 1, 2. So that is the answer for this problem. Next problem is problem 3. For the matrix A equal to 1, 1, 1, 1, 2 minus 3, 2 minus 1, 3 is the square matrix of order 3, because there are 3 rows and 3 columns. Okay, we have to show that a cube minus 6a square plus 5a plus 11i equal to 0 matrix. So the same problem as we have discussed in the previous slide. Okay, so first we have to verify that whether this matrix equation is satisfied or not. Okay, then we have to find A inverse. So in order to verify this, I have to find A cube, A square. Okay, so first I am finding A square. What is A square? A square is A into A. So matrix multiplication, write A 2 times. Then fix the first row in the first matrix. Okay, then first row with first column gives you the first element. First row, second column gives you the second element. First row, third column is 1, 3 position. Then second row, first column is 2, 1. Second row, second column 2, 2. Second row, third column 2, 3. Third row, first column is 3, 1. Third row, second column 3, 2. Third row, third column is 3, 3. Like that you have to find A cube. What is A cube? What you are getting? 8, 7, 1 minus 23, 27 minus 69, 32 minus 30, 58. Okay, so A cube, A square I have found. Now substitute the value of A cube, A square. A is the given matrix. What is the identity matrix here? Identity matrix of order 3. So how will you write that? 1, 0, 0. Okay, 0, 1, 0, 0, 0, 1. Okay, so this is the identity matrix of order 3. Substitute everything is simplify, what you're getting is 0 matrix. Okay, 0, 0, 0, 0, 0, 0, 0, 0, 0. So it is O. 0 matrix of order 3. So we have verified this condition. Next I have to find A inverse. So for that what I have to do? I have to multiply this equation, post multiply. Okay, post multiplying this equation on both sides by A inverse. So A cube into A inverse, A square into A inverse, A into A inverse, I into A inverse. Okay, A cube, this is actually A cube. Okay, what is A cube into A inverse? A cube into A inverse. Okay, so here the base is same, so we can add the power. 3 minus 1 gives 2, so A square. Okay, here we have A square. Okay, A square into A inverse. So what is 2 minus 1? It is A. Base is same, so we can add the power. 2 minus 1 is 1, so A. Next, A into A inverse is an identity matrix, so I. What is I into A inverse? When you multiply any matrix with an identity matrix, then you will get the same matrix. So A inverse. Bring this 11 A inverse to the other side, to the right hand side, you will get minus 11 A inverse. Okay, our A inverse equal to minus 1 by 11 into, this is A square minus 6A plus 5A. So I have got A inverse. What is my A inverse? A inverse is minus 1 by 11 A square minus 6A plus 5A. So I have to substitute A square A I here. Already I have found A square value. A is the given matrix and I, we know that it is an identity matrix of order 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. So substitute everything here and multiply with minus 1 by 11. You will be getting the value of A inverse. So I have substituted everything and simplified. Then what I am getting is minus 1 by 11. This is on simplification 3 minus 4 minus 5 minus 9 1 4 minus 5 3 1. Bring the minus sign inside the matrix. So you'll be getting minus 3 4 5 9 minus 1 minus 4 5 minus 3 minus 1. So this is your A inverse. Thank you.